So then once we establish the design wind speed V for our site, then we go to step 3, and it is the determination of all wind load parameters or coefficients. So first is the wind directionality factor KD, which accounts for the reduced probability of maximum wind coming from any given direction, and also the reduced probability of the maximum pressure coefficient occurring at any given direction. So there is a probability that our particular direction of our structure doesn't experience the maximum wind, because maximum wind direction can be different from the direction of our structure in which we are analyzing our building. So therefore there is a factor accounting for that, and that is called wind directionality factor. For the different structure types, this factor is provided in this particular table 26.6-1. So you can pick, based on the main wind force resisting system, you can pick 0.85 here, or for other kind of structures you also have a number less than 1. For some structures like round or octagonal chimneys or tanks, the value is 1, which means no reduction based on the probability of maximum wind coming from any direction. But for most of the other cases, the number is less than 1, so there is a reduction which is accounted using this factor. Then in the same step 3, we also have to classify our building based on exposure. So we have to give an exposure category to our site, and that exposure category is dependent on what we call as the roughness, surface roughness. So first we will categorize the surface roughness based on this particular provision, and then using the building height and the surface roughness, we will develop or determine the exposure category of our building using this 26.7.3. So first let's discuss about how to classify surface roughness based on the category B, C or D. So there are 3 surface roughness categories. So for each selected wind direction at which the wind loads are to be determined, the exposure of the building or structure shall be determined for the 2 upwind sectors extending 45 degrees on either side of the selected wind direction. So for example, this is your site and this is the direction of wind. So 45 degrees from this side, and then 45 degrees from the other side, 45 degrees. So this is the sector which we should consider, the roughness of which we should consider and classify, and then use it further to determine the exposure category. So surface roughness B means that you have an urban or suburban areas, and then wooded areas or other terrain with numerous closely spaced obstructions, and that have the size of single family dwellings or larger. Then surface roughness C means open terrain, and then D means flat unobstructed areas. So depending upon what area is surrounding your site, you will classify surface roughness as B, C or D. Obviously B is the is rough, highest surface roughness. D means flat or unobstructed areas. So this roughness will affect the design wind speed at our the design wind pressure at which is experienced by our structure. Then once we establish the surface roughness, then we go to the exposure category and assign an exposure category to our structure. So that is a very detailed guideline of how we assign us exposure category, but let me try to simplify that one. So for buildings or other structures with a mean roof height less than or equal to 30 feet, exposure B will be applicable if the surface roughness is also B. Exposure category B will be assigned if the surface roughness is also B in the upwind direction for a distance greater than 1500 feet. And then for buildings and other structures having a height greater than 30 feet, B shall apply when you have a surface roughness B, and at the same time you have and that surface roughness B should prevail for a distance greater than 2600 feet or 20 times the height of the building, whichever is greater. Let me explain that in the form of a figure, which is also available in this particular reference. I have taken it from the commentary of ASCE 7-16, the commentary of chapter 26. So the idea is that if, let's say, this is your building and this is your wind direction, so this is your upwind side. This whole thing, this whole area is your upwind side. So let's say small h is the height of your building. So you are looking at the surface roughness on this side. So let's say that for distance D1, you have a roughness category B, which means very small buildings, one-story buildings, closely spaced buildings. For height of your building less than 30 feet, if D1 is greater than 1500 feet, then you assign it as an exposure category B. Or if your building's height is greater than 30 feet, then D1 should be the greater of 2600 feet or 20 times the height of the building. If any of these two these conditions are fulfilled, depending upon your height of the structure, if it is less than 30 feet, then this first condition should be fulfilled in order to classify this as the exposure B. Or if your height is greater than 30, then this condition 2 should be fulfilled in order to get classified for exposure category B. So if any of these two conditions, depending upon height of the building, fulfills, then you assign an exposure category B. So you have to check that for how much distance your surface roughness B extends from the face of your building towards the upwind side. And if that distance is greater than this number or this number or this number, depending upon the height of the structure, then you classify this as the exposure category B. There are similar guidelines about the exposure category D also, and if the exposure category B and D doesn't applicable to your structure, then you assign it an exposure category C. So therefore, and you should remember that the design wind hazard maps, they were also developed for exposure category C. So now let's discuss how you should classify exposure category D based on the surface roughness. So there are two cases for exposure category D. One case is that you have the roughness category D, and that distance for which the roughness D is prevailing is greater than 5,000 feet or 20 times height of the building. If this is your case, you should assign it as a exposure category D. And please remember, what was roughness D? It was all flat terrain, right? Similarly, this is the second case where you can assign the surface roughness. For example, here that you have the roughness B or C for a distance D2 and roughness D for a distance D1. If D1 is greater than 5,000 feet or 20 times height of the building, and D2 is less than greater of 600 feet or 20 times height of the building. If these conditions fulfilled, again you can assign a exposure category D for your building. So which means that exposure category D can be assigned to surface roughness D as well as surface roughness B or C, depending upon which of these two conditions, A or B, are being fulfilled by your particular site and building. So if again this criteria is not fulfilled, which means exposure category B, or any of these two criteria are not fulfilled, which means exposure category D, then you can assign a exposure category C to your structure. So the summary is that based on your roughness category B, C or D, and for how much distance those roughness categories are extending from the face of the building to your upwind side, and how much is the height of your building, based on these three things you will be assigning the exposure category B, C or D to your structure. So this is how you will be assigning the exposure category to your site and structure. Then topographic factor, it is a factor which accounts for the topography of your site at which your building is located. Sometimes based on the topography of your structure, if it is located at some hill or in some valley, for example, the winds may speed up, and that effect should be accounted using this factor KZT. So, but you should first check whether your site is it should be applied with the topographic factor or not. So, if your site is fulfilling all of these conditions from 1 to 5, then you should apply for these Ks at T. If your structure is not meeting all the conditions specified in this particular 26.8.1, then Ks at T will be simply equal to 1. So let's quickly sweep through these conditions which should be fulfilled in order to calculate this Ks at T. First, the hill, ridge or escarpment, which is the abrupt change in the topography, is isolated and unobstructed upwind by other topographic features of comparable height for 100 times the height of the topographic feature. So if your escarpment have a height of capital H, or if your ridge or three-dimensional hill have a height of capital H, then there is a condition on in the form of that H also that should be fulfilled in order to fulfill this condition 1. So the second is that first is that it should be isolated or unobstructed upwind by any other topographic feature of the same height for this much you can say distance, 100 times the height of the topographic feature, or 2 miles, whichever is less. So please you should check that if there are other topographic features available around your site, then this condition is not fulfilled, which means your escarpment, your hill or your ridge is not isolated. And then again the second condition, it protrudes above the height of upwind terrain feature within this duration, with this radius. The building or other structure is located as shown in this figure in the upper one half of the hill or ridge or near the crest of the escarpment. So this is the condition which should be followed. Then capital H over L sub H should be greater than 0.2. This actually is the slope of your hill or your escarpment. So L sub H is the horizontal distance, capital H is the vertical height. So this becomes the slope. If it is greater than 0.2, then you should go for calculating Ks at T, along with if all the other conditions are also fulfilled. And finally, the capital H is greater than or equal to 15 feet for exposure C and D, and should be greater than or equal to 60 feet for exposure category B. So if all 1 to 5 conditions are fulfilled, then you should use this particular expression to determine Ks at T. Otherwise, Ks at T will be equal to 1. So now these K1, K2, K3 are the 3 coefficients which are required to calculate Ks at T, and they are directly given using an equation and a table here. So K1 is determined from this table directly at the bottom. So depending upon your type of hill, its shape, and then depending upon the exposure category B, C or D, you will directly pick this factor K1 over H over LH, which means K1 over the slope of your escarpment. So depending upon your capital H and your L sub H, you will calculate K1 from this number which you pick from this table. So K1 is directly determined from this table. K2 and K3 will be calculated using these two expressions, and the factor which is mainly required here is this mu, that is also prescribed in this particular table. So upwind of crust, downwind of crust, depending upon that, the factor mu is directly taken from this table. X is the horizontal distance. This is the horizontal distance, and similarly other factors you can see here from these two figures. So all the things, every factor is available. You directly calculate k1, k2, k3. If you want to calculate k's at t and all of the 5 conditions are fulfilled, then you can use this table and this figure to determine k's at t. So for different heights, h over LH, height of an escarpment divided by horizontal distance, the K1 multiplier, K2 multiplier and K2 multiplier for other cases, it is directly prescribed in this table also. So all of the notations here are explained, they are here shown in this particular figure also. Then you have the ground elevation factor. It accounts for the ground elevation as the name indicates. So depending upon the ground elevation above the sea level in feet or in meters, you have this factor. So as we go higher, we have a lesser ground elevation factor. So for it is permitted to take k equal to 1 for all elevations also. So if you want, you can use this guideline, and then there are some notes to use this particular table also. So then is the gust factor. It accounts for actually the loading effect in the along wind direction caused by wind turbulence and structure interaction. So this factor do not account for the allowance of across wind loading, vortex shedding or instability caused by galloping or flutter, or any amplification of aerodynamic torsion caused by building vibration in a pure torsional mode. It only accounts for the loading effects in the along wind direction caused by the wind turbulence structure interaction. So for structures susceptible to loading effects that are not accounted in the gust factor, information should be obtained from recognized literature from wind tunnel test. So this factor is a factor which account for wind turbulence structure interaction. It will not account for the across wind loading. It will not account for vortex shedding or instability caused by galloping or flutter, and also it will not account for aerodynamic torsion. So this factor G is taken equal to 0.85 for rigid buildings. Rigid building is defined as a building having a fundamental frequency greater than 1 Hertz, which means having a natural time period, fundamental mode time period less than 1 second. And alternatively, you can also use this very detailed expression to calculate this gust factor. So otherwise you can also go for just 0.85 for your building. So the detailed expression actually involves several of the factors, for example, intensity of turbulence and different heights. I will not be going into detail of the calculation for gust factor. In most of the practical cases, the 0.85 is used for rigid buildings. But if your building is flexible, which means it is more sensitive to dynamic loading, then you should have a GF factor instead of G factor. GF should be calculated using a very detailed expression, and which requires a lot of inputs, including the dynamic properties of your building also. So that expression is this one. For rigid buildings we know already, but for flexible buildings we have this GF expression, this whole expression. So it requires the fundamental natural frequency and a lot of other factors which are explained within the same 26.11.5. So it is self-contained, although I am not going into detail of these things, but you can find easily what will be the value of a particular coefficient either using an equation or a table which is there. So for example, this 26.11-1 prescribes for different exposure categories. It prescribes different factors which are required to be used here in the previous formulation to determine finally the gust factor for your building. So for flexible buildings, you cannot use 0.85. You have to calculate it depending upon the dynamic characteristics of your building. So then the enclosure classification, as I have said in the start, that you should classify your building either as a enclosed building, open building, or partially enclosed building. So there is a specific guideline about how you should classify them. For example, a building that has a total area of openings in each wall that receives positive external pressure less than or equal to 4 square feet or 1% of the area of that wall, whichever is smaller. In that case, you should classify that as a building which is enclosed. So A naught is the area of opening and AG is the gross area of a particular wall. So if A naught is less than 0.01 AG or 4 feet, whichever is smaller, then you should classify your building as an enclosed building, less than 1% of the gross. Open building, if the A naught, which is the area of opening, is greater than 80% of the gross area. In that case, you should classify it as an open building. The expression to calculate design wind pressure P for open and enclosed is different. And then you also have a partially open or partially enclosed. Actually, partially open is not, the expression is not different. Partially enclosed and enclosed have the same expression. So a building that complies with both of the following conditions should be classified as partially enclosed. The first condition is that the total area of opening in a wall that receives positive external pressure exceeds the sum of the area of opening in the balance of the building envelope by more than 10%. And then second is that the total area of opening exceeds 4 feet square or 1% of the area of that wall, whichever is smaller. And the percentage of opening in the balance of the building envelope does not exceed 20%. So this is explained in these 2 or 3 lines. First condition is that A naught area of opening should be greater than 1.1 times of A naught I. A naught I is what? It is the sum of the openings, sum of the areas of openings in the building envelope, not including A naught. And the second condition says that A naught should be greater than 4 feet square or 10% of AG, whichever is smaller. And at the same time, this ratio A naught I over AGI is less than 0.2. A naught I is already explained. AGI is the sum of gross area, surface area of the building envelope, not including AG. So it is that the percentage of opening in the balance of the building envelope. So if this ratio is less than 0.2, then this condition is also fulfilled, and if both of them are fulfilled, then you should classify it as partially enclosed. Then finally in step 3 we have the step 3.6 finally, and that is the determination of internal pressure coefficient. The main wind force resisting system and component of components and cladding, the GCPI or the internal pressure coefficient for either enclosed, partially open and open buildings is determined from this particular table. For enclosed buildings, for example, this is the criteria to be classified as enclosed building, and the internal pressure is moderate, and these two coefficients are recommended in positive and negative coefficients. Similarly, partially enclosed, these two, then partially open, this one. Open building, no internal pressure coefficient, the expression is different. It doesn't involve the use of GCPI, so it is 0, which means the internal pressure coefficient internal pressure for the open buildings is negligible or zero because it is already open, so no internal pressure is developed. Then we will go to the step 4, which is the determination of velocity pressure exposure coefficient Kz or Kh, depending upon what height it is calculated. So again I repeat that Z denotes any height level denoted by Z, and H denotes a height which is the roof level of your building. So it is dependent on the height at which you are calculating this factor. So based on the exposure category, it is B, C or D, and based on the height above ground level, you will determine directly the value which is the velocity pressure coefficient Kz or Kh from this table 26.10-1. Step 5 is the the determination of the velocity pressure. This is one of the main steps of the calculation of the design wind pressure P, and in this you will be combining all of those coefficients which you have determined earlier and the design wind velocity which you have determined based on the risk category of your building and the hazard level of your building. Here you actually combine all of them in this particular expression. It is an empirical expression, so it depends on the units. So the 26.10-1 is in the miles per hour, where velocity is in miles per hour, and this is in the SI units where velocity was in meter per second. So the pressure coefficient will be in Newton per meter square. So velocity pressure will be Newton per meter square in this particular case. So the empirical factor is different for both cases. So you will be using Kz, which you calculated, Kzt, Kd, Ke, all of them are calculated already, and then velocity is determined from the wind hazard maps. So you multiply all of them in this expression to finally calculate Qz. So Qz, obviously the factor, for example this one, Kz or Kh, velocity pressure exposure coefficient, is different for different heights. So therefore you can calculate this Qz for different heights, right? You can also calculate it for the roof height level, mean roof height of your building. In that case it will be called QH, Q sub H. For any other height it will be denoted as Q sub Z. So we should note that the basic wind speed which we are using here, used in the determination of design wind load on rooftop structures, rooftop equipment and other building, shall consider the risk category equal to the greater of following. The risk category of the building on which that equipment is installed, and the risk category of any facility to which the equipment or that appurtenance provide a necessary service. So for those buildings which are having some special feature, some specific equipment or some specific you can say function, then we can check that we have to provide the greater risk category to that building, greater of these two. The risk category of that equipment itself, of that building itself, and then risk category of that facility to which that equipment provides the service. So we should keep that consideration in mind while selecting the risk category. So all the notation is clear now. We will finally be determining the velocity pressure Qz or QH depending upon what height we determine it using in that particular expression. So the step 6 is the determination of external pressure coefficient. So if you remember, the expression for P was actually it was the product of Q and then the gust factor and then this Cp, and there was an internal pressure also which was in minus. For open buildings that second term was not there. So the final step in before we can actually determine this design wind pressure is the determination of external pressure coefficient. and that external pressure coefficient is dependent on your building plan or aspect ratio actually. So if capital B is the width is one dimension of your structure and capital L is the other dimension in plan view, then this ratio B over L or this aspect ratio will affect the distribution of external pressure coefficient. For regular building, a square kind of a building, we will have a very regular distribution of external pressure Cp. So we will be having this pressure in the windward side and this one in the leeward side. For having for this kind of a roof, if this is elevation, you can see the external pressure will be like this, or this kind of an elevation it will be in this direction, particular this direction. For this kind of a slope, two slopes, we will be having this. So depending upon our aspect ratio, our dimensions of our structure, the ASCE 7-16 will guide us about what CP we should be using. So these are also two other roof configurations. So please remember this classification, this notation in mind, because next I'll be explaining this table to pick these CP values, and that table actually requires the aspect ratio L over B. So L is the horizontal dimension of the building in measured parallel to the wind direction, and B is the dimension of the building measured normal to the wind direction. So you determine these two dimensions of your building, and then depending upon L over B ratio and which surface you want to apply, the CP coefficients are there. So this number you have to pick from this particular table. And then there are a series of figures also. I only show here one simple case, but for each of these types of structure we have different tables where we can pick CP. So these tables you can review and then finally extract or pick your CP coefficient. For open building, that CP was for enclosed or partially enclosed building. For open buildings, we have a net pressure coefficient Cn, which is required in that empirical expression to determine the design wind pressure. So depending upon our roof angle, for example, 0 means flat roof, and then it goes up to 45 degrees. And then we also have a load case A or B, which is defined in the same specific provision. And wind direction 0 and 180 degree, which means in one particular side and then for the opposite side. Then again we have a classification about clear wind flow or obstructed wind flow, and then finally the coefficient for these two particular cases, and finally we can go for our particular case and pick the net pressure coefficient. So let me again go back here and okay, this is for CP and this particular table is for CN. These kind of tables are for this particular table is for monoslope free roofs, but we have trough roofs, pitch roofs or other kind of roofs, and there are detailed tables available. You can check ASCE 7-16 chapter 26 and then 27 to find all those tables. So the notations which are used in this particular table, for example, CNW, CNL, roof angle theta or wind angle gamma, all are explained in this figure, right? So they are self-explanatory. For example, roof angle is clear, wind direction is clear, 0 means this side, 180 means opposite side. Similarly, this pressure distribution coefficients they are given. Similarly, other factors are explained in this notation table also. So CNW and CNR and L denote net pressure contributions from top and bottom surfaces from windward and leeward half of the roof surfaces. So this is for windward, this is net pressure coefficient from leeward. So finally we can determine the wind pressure for each building surface. we are in a position now to use this expression finally. Q is determined already, G is established already or determined if the building is flexible. CP is also calculated or determined from the detailed set of tables available in ASCE 7-16. So, and similarly GCPI and QI, they all are calculated now. So we can use this expression 27.3-1 to determine this design wind pressure. Now this wind pressure will be applied to each of the surface which is contributing to the exposure of the building and is converted into the wind force and applied at the appropriate locations of the building depending upon whether you use the rigid diaphragm or flexible diaphragm. So I'll explain that in the software demonstration part. So all of the notations which are used in this expression, they are already explained in previous slides. We can repeat it here, so you can check that one afterwards also. So for this expression was for enclosed and partially enclosed buildings, and this simplified expression is for open buildings. Instead of using CP, we will be using CN, which is the net pressure coefficient, and there is no GCPI, which means there is no internal pressure in the open buildings.